Hi students, welcome to the video lecture 4 on the topic transient heat conduction. So in the today's class, we will solve the problems. So let me read the first problem. A steel ball of a 5 centimeter diameter initially at a uniform temperature of 450 degrees centigrade is suddenly placed in an environment at 100 degrees centigrade. Heat transfer coefficient is H between steel ball and the fluid is 10 watt per meter square Kelvin. For steel, specific heat is 0.46 kilojoules per kg Kelvin, whereas density is 7800 kg per meter cube and thermal conductivity K is 35 watt per meter Kelvin. So he has asked us to calculate the time required for the ball to reach a temperature of 150 degrees centigrade. This is first part, and second part also find the rate of cooling after 1 hour. So here in the problem he has given the steel ball, it is of 5 centimeter diameter, initially having a temperature of 450 degrees centigrade. So when that steel ball is suddenly placed in an environment which is at 100 degrees centigrade, then definitely heat is going to transfer from the ball to the environment. So here we are considering only convective heat transfer coefficient rather than internal conduction heat conduction. So here heat transfer coefficient H also he has given 10 watt per meter square Kelvin, and these are the datas he has given. So let me write here diameter D, he has given it as 5 centimeter. So I have written it in meter here. This is the data given. The temperature Ti, initial temperature of the steel ball is 450 degrees centigrade. It is placed in an environment where temperature Ta is equals to 100 degrees centigrade. This H heat transfer coefficient he has given. Specific heat he has given. Density he has given. Thermal conductivity K he has given, and he has asked us to calculate the time required for the ball to reach a temperature of 150 degree centigrade. So we don't know temperature. So when this the steel ball, when it is initially at 450 degrees centigrade, when it is suddenly placed in an environment of 100 degrees centigrade, then the heat transfer starts. So how much time is required to reach the steel ball of 150 degrees centigrade? We don't know time. At any time t, at what time t this temperature of the ball it reaches 150 degrees centigrade, that he has asked us to calculate this small t in the first part. So before solving the problem, first we have to calculate it's the Biot number. So Biot number, it is given by the formula Bi is equals to H into LC divided by K, where LC is the characteristic length. The problem is based on steel ball which will be having the shape of sphere. So for sphere, this characteristic length LC is given by V divided by A. So if we solve this V divided by A, the formula for characteristics length LC for sphere will be R divided by 3. In the previous lecture already we have calculated it. Characteristic length LC for cylinder, for sphere we have calculated, for plane slab, for cube also we have calculated. So this for sphere, this LC is given by R divided by 3, where R is diameter, half of the diameter, it is 0.025 divided by 3. So this will be the 8.33 into 10 to the power minus 3 will be the characteristic length LC. So this LC will substitute in the formula, it is Biot number. Character H heat transfer coefficient he has given 10. Characteristic length LC we have calculated, it is 8.33 into 10 to the power minus 3 divided by thermal conductivity K, that is 35. So Biot number will be 2.38 into 10 to the power minus 3. So if the Biot number value is less than 0.1, then only this lumped system analysis is applicable. If suppose the Biot number is greater than 0.1, then we cannot solve the problem by using lumped system analysis. Only the Biot number should be less than 0.1, then only we can apply the lumped system analysis for solving the problem. So in order to calculate this temperature T, already we are having the formula. This we have derived it in the previous classes. So temperature T, this to T, while deriving the equation, already we have told this temperature T at any time T means at any time, that is T is seconds, let the temperature of the body be T. So this T he has given here 150 degrees centigrade. I don't know at what time the temperature of the ball is at 150 degrees centigrade. This T already has given. This T minus Ta divided by Ti minus Ta is equals to exponential form of minus H into A into T divided by rho into Cp into V. So with this equation, I can write this equation in this form also, exponential form of minus T divided by tau, that is thermal time constant. We can write the expression in this form also. So this thermal time constant is given by the formula rho into Cp into V divided by H into A. This indicates thermal time constant, but thermal time constant formula is rho into Cp into V divided by H into A. So first let me calculate the value of this thermal time constant, that is rho is 7800 he has given already. Specific heat he has given in terms of kilojoules per kg Kelvin. So in all the problems substitute the specific heat in terms of joules per kg Kelvin. Substitute the value in joules per kg Kelvin. For that purpose here 0.46 into 10 to the power 3, it will be 460 joules per kg Kelvin into this V divided by A. V divided by A is nothing but the characteristic length LC. This LC already we have calculated here. The same value I have substituted here, divided by H, that is heat transfer coefficient remains as it is. So my thermal time constant value will be 2988.8 seconds. Now let me substitute the values here. So T 150 degrees centigrade minus environment temperature 100 degrees centigrade divided by initial temperature of that steel ball is 450 minus 100 is equals to exponential form of minus T divided by this thermal time constant tau, where tau is nothing but rho into Cp into V divided by H into A. So here in this formula it is H into A divided by rho into Cp into V. So for that purpose I have written here 1 divided by this thermal time constant minus T divided by this tau value I have written here. I think hope you have understood this, how I have written this minus T divided by tau. This say by this equation I have written here. So tau value already we have calculated here. So if I will shift this exponential, because this term here is unknown, so I cannot calculate by using this formula. So I will I will remove this exponential form and I will write the equation in this form, that is log form. So in the previous derivation, this log only we have removed the log and we have written the equation in terms of exponential form. So I will write this equation in this form. It is log of 150 minus 100 will be 50, 450 minus 100 will be 350. So minus T divided by 2988.8. So by solving this equation, I am going to get the value of temperature as 5818 seconds. So divided by 3600 if we will do, then we are going to get the time T in hours, that is 1.616 hours. So this much time is required to cool the temperature of the ball up to 150 degree centigrade, or 1.616 hour is the time required to calculate that is the time required for the ball to reach a temperature of 150 degree centigrade. Now next part, also find the rate of cooling after 1 hour. Yes, asked. So if you ask the problem in this way, so first with this equation I have written the equation, that is temperature. This indicates temperature T at any time T. So T of T is equals to Ta plus Ti minus Ta into exponential form of minus H into A into T divided by rho into Cp into V. With this equation only I have written this equation, because I want to calculate the rate of cooling, this temperature time T, temperature T at any time T after 1 hour. So if I want to calculate the rate of cooling after 1 hour, let us differentiate this equation with respect to time. So this will be dt upon dt, that is change of temperature with respect to change in temperature for 1 hour, that is for 1 hour it will be 3600 seconds. So if I will differentiate this equation, this is constant term, this is 0. So if I will differentiate this equation with respect to T, then I am going to get the differential form of this equation in this form. It is Ti minus Ta into minus H into A divided by rho into Cp into V. This term becomes constant into exponential form of this term remains as it is. This term remains as it is. That is differentiate d upon dx of e to the power x term. How we will define that? D upon dx of e to the power x term. If we differentiate that we are going to get in this form, x into e to the power x. The same form we have written this equation. So let me substitute the values. Ti is 450 minus Ta is 100. So H value is 10. So this A divided by V. So already this V divided by A, characteristic length LC is nothing but V divided by A. V divided by A, only I have got this value, that is 8.33 into 10 to the power minus 3. So if the same equation, if I want to write in this form of A divided by V, so if I will write the equation, or we can write this as 1 divided by LC term also. A divided by V is nothing but that is LC I can write in this equation, or the reciprocal of this. So if I will solve this A divided by V, that is 1 divided by LC term, then I am going to get this 120 answer divided by rho into Cp as it is. So exponential form of minus 10, this is A divided by V. I have got 120 value. T is 3600 divided by rho value, this 7800 into 460. This is specific heat. This A divided by V term. So let me explain once again. Characteristic length LC is given by V divided by A. Here the equation is in this form, A divided by V. So I can substitute in the form of A divided by V term by calculating. I am going to get 120, or otherwise V divided by A term only I can substitute here. In this equation denominator only I can substitute this 8.33 into 10 to the power minus 3. So by solving this entire equation, I am going to get the value as minus 0.03506 degree centigrade per second. So this much degree centigrade the rate of cooling is there for per second. So why we have got here negative sign? As time increases, temperature decreases. For that purpose we have got here negative sign. So let me go for the next problem. Similar type of problem, but in the previous problem the problem is based on sphere. Here the problem is based on slab. Let me read the problem first. A 50 centimeter into 50 centimeter copper slab, 6 mm thick, at a uniform temperature of 350 degrees centigrade, suddenly has its surface temperature lowered to 30 degrees centigrade. So find the time at which the slab temperature becomes 100 degrees centigrade. Given density is 9000 kg per meter cube, specific heat Cp is 0.38 kilojoules per kg Kelvin, where thermal conductivity K is 370 watt per meter Kelvin, where H is 100 watt per meter square Kelvin. Also find the rate of cooling after 60 seconds. So similar type of problem this is. Only thing the problem is based on here slab. So again here thickness of the slab he has given it as 6 mm thick. The initial temperature of the slab, uniform temperature of the slab, that initially it is at 350 degrees centigrade. So when it is suddenly placed at a surface temperature which is lowered to 30 degrees centigrade, that is TA, environment temperature, that is 30 degrees centigrade. And what is the time required to calculate, what is the time required to cool the slab up to 100 degree centigrade? What is the time required? He has asked us to calculate. So here first let us calculate here also the Biot number. Biot number Bi is given by H into Lc divided by K, where Lc is the characteristic length. For plane slab, where characteristic length Lc is given by V divided by A. By solving that I am going to get the value as L only. Well is that L indicates half the thickness of the slab. Already in the second slide only we have discussed about this. LC, that is LC is equals to L, half the thickness of the slab. So thickness of the slab here they have given as 6 mm thickness. So LC will be equals to L, that is 0.003 meter, that is 3 mm. I have written directly it here in meter. Characteristic length LC for plane slab is given, that is V divided by A. If we will calculate it, I am going to get the value as L only, where L indicates half the thickness of the slab. So slab thickness is 6 mm given in the problem. So half the thickness of the slab will be 3 mm. So I have directly converted it in meter here. This will be 0.003 meter. So after this, let us calculate the Biot number. So H is 100, LC is 0.003 divided by, this is 380. Sorry, this is here 380. It should be 380. So if we will solve this, we are going to get the value as 8.108 into 10 to the power minus 4. So here I should write here 380 instead of 380. We have written here 370, but answer is correct. Next, so when Biot number is less than 0.1, so lump system analysis is applicable. So with this formula, we'll calculate this time T. How much time is required to cool the temperature of the slab up to 100 degrees centigrade. So here I will substitute the value. So I will remove this exponential term and directly I will write the equation in this form only. So this temperature T is 100, means up to reaching the temperature of 100 degrees centigrade, what is the time required for the slab? 100 minus 30 divided by 350 minus 30 is equals to minus T divided by 102.6. So this value I have taken it from here. So the same equation I have written in this form, as exponential form of minus T divided by tau here, where tau indicates rho into Cp into V divided by H into A. In the previous problem already we have explained it. Tau is nothing but rho into Cp into V divided by H into A. So here it is H into A divided by rho into Cp into V. For that purpose I have written here minus T divided by tau. That is thermal constant tau is given by rho into Cp into V divided by H into A. The same equation I have written here. So let me calculate first the value of this tau thermal time constant, where tau is 9000, density is 9000, Cp specific heat is 380, V divided by A, that is nothing but characteristic length LC. That LC is nothing but only 0.003 I have substituted here. V divided by A directly I have substituted here, divided by only one term is H. H I have substituted as 100. So this thermal time constant will be 102.6 seconds. The same value I have substituted here, the same exponential form minus T divided by tau. So as I have removed exponential form, I have taken here log term to this side. So again by solving this equation, I am going to get the value of T as 155.93 seconds. So this is the time required to cool the temperature of the slab up to 100 degree centigrade. If I convert it in hours divided by 3600, so this will be T is equals to 0.0433 hours. So now next part, again find out the rate of cooling after 60 seconds. The same equation, with this equation only I have written this equation. T of T is equals to Ta plus Ti minus Ta into exponential form of this term. Again if I will differentiate this equation with respect to temperature, so this term becomes 0. So differential form of this equation will be in this form. So again I will substitute the value here. Ti is 350, Ta is 30 into minus of H is 100. So A divided by V. See here I have clearly written here. V divided by A, that is characteristic length LC, is nothing but 0.003. Character LC is nothing but V divided by A. V divided by A only I have got it as here 0.003 meter, or L, that is half the thickness of the slab. So here in the problem it is A divided by V, where A divided by V I will get 1 divided by of this answer. So this will be 333.33. So the same value I have substituted here. H is 100, A divided by V itself is 333.33 divided by density is 9000 into specific heat is 380. Exponential form of again H is 100, A divided by V term, that's calculated A divided by V term only I have substituted 333.33. Time is 60 seconds. Rate of cooling for 60 seconds, that T I have substituted here as 60 seconds divided by density is 9000 into specific heat is 380. So the time I am going to get it as minus 1.823. So here also negative sign indicates as time increases temperature falls. For that purpose we have written here negative sign.